Kia ora, Year 12. This is a quick video going through probability density functions, which is what I started to talk about at the very end of today's class. This is the first part of chapter 10 of the textbook, and it's an idea that sounds quite complicated at first, but one that we've actually been using without knowing it. So here's where we've been using it, and that's in the normal distribution. So when we find probabilities from random variables that are continuous, then we use the idea of a probability density function. So if I asked you to find a probability here, suppose that mu was equal to 30 and sigma was equal to 10, and I said find me the probability that x is less than 45, we could draw that picture here, make this 30, and we'd be looking for the area under the curve. Now, when you guys learned how to do this, you didn't know how to integrate, was probably back in about year 10. And you just either looked this up in a table or sometimes you did it on a computer or a calculator. And what the table and the computer and the calculator were doing was using what we call numerical methods, which we know about from Pure 3, to find that probability. What we're going to do in chapter 10 is work with PDF's probability density functions that are simple enough that we can do the integration ourselves. So this is the pretty cool but hard to integrate normal density function. And you won't see that again until probably second or third year of uni. So we're not going to use that one this year, but it's a good way to start thinking about what a PDF is. What we're going to do now is do a little bit of stuff using some simpler functions. Okay, so all this says is what I've just said. At A level, we are going to be doing what the table does, but using functions that we can integrate. And there are two big things that we have to check to make sure that a function might be a PDF. The first thing is that the area under the curve has got to add up to 1, right? Because probabilities always do that, except for the level 3 stats exam a couple of years ago, but let's not worry about that for now. So the integral has got to equal 1, and that means that we're often going to have to figure out this, the integral from infinity to negative infinity of f of x with respect to x. And again, this looks awful until we think that actually often we're going to be dealing with situations where we're told that the domain of the function is between a couple of places. So it's, for example, 0 to 3, f of x has this shape. Everywhere else it's defined to be 0. So that simplifies my integration straight away. The other thing we often have to check is that my function has to be either 0 or positive. So what I'm going to do now is quickly work through this example, and this is question 3 from textbook 10A. So my PDF has been given to me as f of x is equal to a x cubed, but we don't know yet what a is. So the first part of the problem, and in some ways the hardest, is to figure out what a is that's going to make this thing a PDF. Now, the thing I forgot to put in here is that f of x is equal to that for x between just 0 and 3, and f of x is equal to 0 elsewhere. Okay, so first we're going to figure out what's the value of a, the constant, then we're going to graph it, and then we're going to use it to find this probability. It shouldn't take too long. Just be patient. Right, so the first thing we need to do is we have to figure out for what value of a will this integral be equal to 1. But that's not quite right, because this is not defined for all of these values. So let's back up, cross that out of your book. This is what we want to do. We want to say that the integral of the PDF has to be 1. Not exactly the same thing. It's the same as saying the integral from 3 to 0 of ax cubed dx is equal to 1. And you can see that this is now a really simple little integration problem. So we get a over 4, x to the power of 4 is equal to 1. So it's about an achieved or merit level 3 integration question. Evaluating it at the two limits, we get a over 4 times 3 to the 4, which is 81, minus 0 is equal to 1. So a works out to be 4 over 81. Okay, so the first part of the problem is done. F of x is going to be equal to 4 over 81 x cubed for x between 0 and 3, and it's equal to 0 elsewhere. It's a really good habit to get into, not to forget to write that down. Okay, so just to make it really clear that you've really got the idea that there are limits on the domain. Okay, so that's the first thing. The second thing, a pretty obvious thing, is to let's draw a wee graph of this and see what it looks like. So I've done that in GeoGebra, except that I accidentally chopped off the axes. But this is it. This is f of x is equal to 4 over 81 x cubed for x between those two values. And then the last thing we're going to do is we're going to find the probability that x is less than 2. So what we're looking for is that integral there. So the probability that x is less than 2 is equal to this. So we're going to get 4 over 81, x to the power of 4 over 4, evaluated at 2 and 0, which gives me 16 over 81. And then you can work that out as a decimal. And that's it, we're done. Okay, so most of 10A is problems along those lines. I'll try and do work solutions tonight. After that, we've got 3 more skills that we've got to learn that I'm not going to put into this video. We've got to find the mean, the mode, and the median using a PDF. Now, I'm going to show you the coolest one now, because I can't help it, which is how to find the mode. So just one more little slide on this, and then I'm going to stop. So suppose that I've got this curve, which is not a normal curve. This is just some PDF. So where is the mode? Well, the mode is, loosely speaking, at the top. And what do we know about where that happens? Well, that's where the gradient is equal to 0. Okay, so if you want to read ahead in the book, have a look at the next part where we do the mean, median, and the mode. Otherwise, go and have a go at exercise 10A, either tonight if you're watching this now or tomorrow in class if you're normal. Thanks for watching.